today's learning objective. By the end of this session, you will be able to solve systems of linear equations using Cramer's rule. So we will consider the following 2x2 system. The first equation, ax plus by equals e, and the second equation, cx plus dy equals f. Now we want to solve this system, so we will multiply the first equation by d to give us the following. And the second equation, we're going to multiply by minus b to give us the following. The reason we did this is because we're trying to eliminate the variable y. As we can see in the first equation, we'll have this term plus b dy. And in the second equation, we have the term minus b dy. So therefore, we can solve for x by elimination. So what we will then do is we'll add the two equations here to give us the following. And then to solve for x, we just need to divide by this term here, AD minus BC, which is a constant term. And therefore, we find that x equals the following. Now, a similar approach will give us y equals the following. Let's consider the denominator in this fraction here and in this fraction here. So if we consider the denominators are the same, it's AD minus BC in the x solution and the y solution. Now, if we consider the coefficient matrix of this system, A, B, C, D, a 2x2 matrix, we see that AD minus BC is actually the determinant of the coefficient matrix. So let's summarize. We should recognize the denominator of each fraction, so the denominator AD minus BC, as the determinant of the system's coefficient matrix A, given by the matrix here. Indeed, the determinant here will be A multiply D, AD, minus B multiply C, BC. Now we'll move on to the next slide. We'll look at the numerator, and we can see that we can also express this as a determinant. So coming on to Cramer's rule, let's just revisit the system from the previous slide. Indeed, this is the system. And when solving the system, we found x equals the following and y equals the following, where A was indeed the coefficient matrix of the system, given by this 2x2 matrix here. And what we said was that the denominator here in the x solution and the y solution is the determinant of the coefficient matrix. So now let's consider the numerator. So first, well, we will write that x equal ed minus fb divided by ad minus bc from here. And let's see how we can express the numerator and the denominator both as determinants. Now, we know that the denominator is the determinant of the coefficient matrix. So here we have the determinant of the coefficient matrix A. Now, if we look at the numerator, if we replace the first column of the coefficient matrix, that is the constant A and the constant C, with these constants E and F, which come from the two equations, the system of equations that we're trying to solve, the constants E and F, we see that the determinant of this new matrix here is indeed ED minus FB. Now this is, of course, this term here, the numerator of our solution. So what we've done is we've replaced the variables or the coefficients of the x with the constant terms in our system. So therefore, we'll call this determinant the determinant of A of x, where A of x is the coefficient matrix with the x coefficients replaced by our constant terms E and F. Now, if we look at the y solution, again, we can express y in a similar way. So indeed, the numerator now is AF minus CE, with the denominator the same as for x. So focusing on the numerator, we can see that AF minus CE is the determinant of the matrix with entries A, C, E, F. So what we have done now is we have replaced the coefficients of the y variable, namely BD, with the constant terms E and F. So we can see that AC is still there, and instead of BD, we have E and F. So we will call this the determinant of matrix A of sub y, where the y coefficients have been replaced with the constant terms. So now what we have here, we can follow on and summarize what we found. we notice that the numerators, the determinant of a sub x and the determinant of a sub y, are the determinants of the matrices formed by replacing the coefficients of x for a sub x or y for a sub y, respectively, in the coefficient matrix with the column of constant terms with entries e and f, which of course come from our two equations here. So in the first column, because x is the first variable, we replaced a and c with e and f. So a and c were replaced by e and f. Now y is the second variable, so the second column now will replace with e and f. So b and d have been replaced with e and f. And we can extend this further for 3x3 systems, 4x4 systems, and so on. Now, as I said already, this method for solving square systems through determinants is known as Cramer's rule. And of course, Cramer's rule can also be used to solve more complex systems. We'll move on to this in the next slide.
Now before we continue, please don't forget to like the video and subscribe to our channel. As a reminder, we offer private and group online math lessons on Zoom. The first session is always free. We cover all UAE National Curricula, American and British curriculums. We also have the best MSAT math test preparation course with a 50% discount for groups. So if you are interested in a free lesson, click the link in the description below and send us a message now. Okay, with that said, let's get back to our lesson.
Generalization of Cramer's rule. We will consider a system of n equations in n variables. We let A be the coefficient matrix of a system of the n linear equations in n variables given by the matrix equation AX equal B. A is the system's coefficient matrix. It is a n by n matrix. X is a column vector containing the variables. And B is the column vector containing the constant terms. So in the 2x2 case, X contained the variables X and Y, so big X that is, and the column vector B contained the constant terms E and F. If the determinant of A is non-zero, then there is a unique solution of the system, and the solution of the system is given by x1, x sub 1, the first variable, equal the determinant of a sub 1 divided by the determinant of A. X sub 2 is given by the determinant of a sub 2 divided by the determinant of A, all the way up to x sub n, which is given by the determinant of a sub n divided by the determinant of A. So this helps us see the relationship between the first variable, solution of the first variable, and how we change the coefficient matrix. So for x sub 1, we replace the first column of the coefficient matrix with the entries from the column vector B. And for the nth variable, the solution for the nth variable, we replace the nth column of the coefficient matrix with the entries from the column vector B. And of course here A sub I rather, is obtained by replacing the ith column of the coefficient matrix A with the column of constant terms B, as I already said. Now, if the determinant of A is 0, then the equation AX equal B has either no solutions or infinitely many solutions. So in this condition, if the determinant is 0, then we can state that there are no solutions or infinitely many solutions. But if the determinant is non-zero, then we do have a unique solution as given by the following equations. Let's have a look at an example now. So we're going to use Cramer's rule to find the solution of the system of linear equations if a unique solution exists. So here's our system, 5x plus 4y equals 7, and minus x minus 2y equal 1. So first of all, we note that the system's coefficient matrix is given by the entries 5, 4, minus 1, minus 2. So we get this from where? The equations here. 5, 4, minus 1, minus 2. So this is the system's coefficient matrix. Then what we need to do, we have to calculate the determinant of this coefficient matrix, called A. So the determinant of A is given by 5 multiplied minus 2, minus 4 multiplied minus 1. And when we calculate this, we get minus 6. Now, since minus 6 is non-zero, that means because the determinant of A is non-zero, we can indeed apply Cramer's rule, as we showed on the previous slide. So now we'll apply Cramer's rule. We have these two terms here, 7 and 1. Just highlight it or underline them. Why? Because this 7 and 1 here is going to be the constant terms that we're going to replace our coefficient matrix with, or the first column and the second column. We'll use these entries 7 and 1. So it's important that we note these, because these are going to help us find the solution. So in the case for the x variable, well, it's our first variable, x, we will say x equal a1 divided by a, or the determinant of a sub 1 divided by the determinant of a. So that means we'll replace the first column, so the entries 5 and minus 1, with the constant terms 7 and 1. So that is the determinant of 7, 1, 4, minus 2, divided by the determinant of a. Now the determinant of a is minus 6, and the determinant here, or the numerator term, is going to be 7 multiply minus 2, minus 4 multiply 1. And when we calculate this, we find that x equals 3. Similarly for y, well, y equals the determinant of a sub 2 divided by the determinant of a. So we now replace the second column of our coefficient matrix, so the entries 4 and minus 2, with the constant terms 7 and 1. So this is what we have here, and upon calculating the determinant here, we have that y equals minus 2. So to summarize, the solution is x equals 3, y equals minus 2. And what we can do is we can also check this answer in the original system to verify it. So you may substitute it in this system, and you will see that the system of equations indeed satisfies this solution. Let's come on to today's task. Use Cramer's rule to find the solution of the system of linear equations if a unique solution exists. So here are your equations. As you can see, you have three different equations. And you have the variables x, y, and z. So at this time, you may wish to consider what your coefficient matrix A will look like. So you can pause the video now, have a go at the question, and when you are ready to continue, please press play. So coming on to the coefficient matrix now, well, of course, you have three variables, so it's going to be 3 by 3 matrix. So the coefficient matrix A is given by the following matrix. So just to demonstrate how we find the first row, of course, we'll look at the coefficients of the variables in the first equation. The coefficient of x is 1, the coefficient of y is 2, and of course there's no z here, so the coefficient of z is 0. And the same for the second and third rows. So then what we must do, we must calculate the determinant of A. So this is a 3 by 3 matrix, so if you don't know how to calculate the determinant of 3 by 3 matrices, you may wish to revisit that topic. But upon finding the determinant of A, we find that it is 19. Okay, and the steps here above is just one way of finding the determinant. So you may know other ways of calculating the determinant of a 3 by 3 matrix, but as long as you get 19, it's fine. Now, because the determinant of the matrix A is non-zero, we can apply Cramer's rule. And before going on to the next slide, which is a continuation of this question, let's look at these terms here, 12, 25, 20. So these constant terms here is what we're going to replace the columns of our coefficient matrix A with. So please make a note of 12, 25, 20 as we continue with the solution of the task. So now applying Cramer's rule, we find that x equals 6. I will just demonstrate quickly how we find this. Well, x equal the determinant of A sub 1 divided by the determinant of A. So here's the matrix A, the coefficient matrix A. So A sub 1 means we replace the first column, so 1, 0, 1, the entry is 1, 0, 1, with the 12, 25, 20, which are highlighted at the end of the previous slide. And then we calculate the determinant of the numerator, or rather the numerator, so the determinant of A sub 1. And of course, we know the determinant of the coefficient matrix is 19 from the previous slide, so we get x equals 6. Similarly for y and z, we get y equals 3 and z equals minus 4. So to summarize, the solution is x equals 6, y equals 3, and z equals minus 4. And once again, it's useful to check this answer in the original system to verify it. So you can check it and you will see that the system of equations satisfies the solution here.